In this video today, we are discussing the application of superposition principle in one more example so as to ensure that we understand the concept well enough. And after that, we will be discussing the new concept, the concept of electric field and electric field intensity. So the example on superposition principle, well, let's consider four charged particles, each carrying a charge plus q, and they are placed on the vertices of a square of side A. Now let's say this point is the origin, and this is the positive x direction, and this is the positive y direction, and we are interested in calculating the net force acting on this charged particle which is placed at the origin. Now the force on this particle due to this particle plus q, let's say that force is F1. This distance here is A, this is A, this is A, this is A. Now this F1 due to plus Q on this plus Q has to be a repulsive force along the line joining them. The magnitude of this force F1 is 1 by 4 pi epsilon naught times Q square by A square. Now that's the magnitude of this force. Once you express this force F1 vectorially, what you'll be getting is something like this. F1 equals this magnitude, 1 by 4 pi epsilon naught Q square by A square times I cap plus this force is in x-axis direction, so its y component will obviously be 0, so we have 0 j cap there. Now this was due to charge 1. Now due to charge 2 and 3, we have two more forces. So we'll be having three different forces. We'll be doing a vector summation of those to arrive at the final result of what we'll call the answer. Now the force on this charged particle due to charge 2, if this distance here is A and this distance is A as well, then using Pythagoras's theorem, we can calculate this length, and this comes out to be root 2 times A. Therefore, the force on this charge due to this charge, let's call this F2. Its magnitude will be given by F2. I'm messing up the colors, but then who cares? 1 by 4 pi epsilon naught into Q square by square of root 2a, that's 2a square. So that's your F2, and once you express it vectorially, well, let's see what we get. This angle here is 45 degrees, and therefore this is 45 degrees as well. The x component of F2 will be therefore this magnitude, 1 by 4 pi epsilon naught Q square by 2a square times cos of 45, which is 1 by root 2 I cap, plus the y component. Now this is again with the y axis as well, it makes a 45 degree angle, so the same magnitude multiplied by cos 45 again. So we have 1 by 4 pi epsilon naught q square by 2a square times 1 by root 2 j cap. That's the y component. Now the force F3 due to charge 3, the magnitude will be exactly the same as the force F1. So we have this 1 by 4 pi epsilon naught q square by a square, and this time your F3 is in positive direction of y-axis. We have the magnitude already, so we'll be expressing it like a regular vector. So 0 I cap, the vector is in positive y direction, so x component is 0, plus we'll have this magnitude of F3, that's 1 by 4 pi epsilon naught q square by a square times j cap. Now the net force will be basically a vector sum of F1, F2 and F3. Now once we add them vectorially, what we get is, now it's pretty simple actually, you add the x components separately. So when you add these three x components, you will get 1 by 4 pi epsilon naught q square by a square times 1 plus 1 by 2 root 2 I cap. So the three x components, this and this, when added give you this quantity here. Similarly, the three y components when added will give you, in fact, the same quantity. So 1 by 4 pi epsilon naught q square by a square times 1 plus 1 by 2 root 2 j cap. You will notice here now that the x and y components of this net force have the same magnitude. Therefore, now when we calculate the magnitude of the net force, we get root fx square plus fy square, and since both of them have the same magnitude, you end up with root 2 times any one of them, say fx. So the magnitude of this net force will be root 2 times any one of these two, fx or fy. So we have 1 by 4 pi epsilon naught q square by a square root 2 plus 1 by 2. That's the magnitude. Also, this is x-axis, this is y-axis, and we have equal magnitudes of fx and fy. And this here, the vector sum of these two, is the resultant f net. If you are to work out its direction, let's say this angle is theta, tan theta of course will be fy by fx, and since fy and fx are equal, tan theta equals 1, which essentially means theta equals 45 degrees or pi by 4 radian. So what we've done is, we've seen one simple example where we've applied superposition principle, and if we can apply it in one situation, we can apply it now in any number of situations. So that then is superposition principle. Now after having studied Coulomb's law and also the superposition principle, we have arrived at a situation where we can actually move on and study the next concept, and that is the concept of electric field and electric field intensity. So we are going to talk now about electric field and later about electric field intensity. What is electric field? Electric field around a charge or around a charged particle or a charged body is the space around it in which its electrostatic influence can be felt by other objects. So in a sense, if we have a charged particle, what it does is it creates a sphere of influence around it. It modifies the space around it. And the space actually gets modified in such a way that any other charge brought inside this space experiences a force. So for instance, if we have a charged particle here or a charged body here, what it does is in some way it modifies the space around it. So we have around it a kind of modified space, and this space, let me kind of, to indicate that it's some sort of a modified space, let me do a bit of shading here. So this is a modified space around the charge. And what is the modification? The modification is such that if we place any other charged object here, let's say this was charge 1, this is charge 2, any other charge brought inside this modified space will experience a force due to charge 1. Let's say they're unlike, so there will be an attraction. So a charged object modifies the space around it in such a way that any other charged object brought inside that space experiences a force. This modified space around a charge in which it can exert electrostatic forces on other charged objects, this modified space is called its electric field. So this electric field can be described as the space around a charged object in which its influence can be felt by other charged objects in the form of a force. So that's the idea, that's the concept of electric field. What a charge does is it kind of modifies the space around it, and it does it in such a way that this modified space then applies forces on other charged objects when they're placed in this space. So you can say that the electric field of a charge is kind of the sphere of influence of that charged object. Now when you're very, very close to a charge, this influence is very strong, and when you move away from it, this influence gets weaker. So this electric field intensity, this electric field is more intense or stronger when you're close to it, when you're close to a charge, and as you move away, it weakens. Now to measure how strong or weak it is, we have to define another physical quantity, and this physical quantity it's a vector. It's called electric field intensity. We will be representing it as E, and as I said, it's a vector quantity. The electric field at a given point, let's say this point here is P, and we are interested in working out the electric field intensity at point P. Now, to work out the electric field intensity at point P, what we have to do is we have to bring a positive test charge Q0 and place it at point P. So to measure the electric field intensity or electric field strength, some people call it electric field strength, mostly electric field intensity. Now to measure electric field intensity at point P, what we have done, we brought a charge, test charge, plus Q0 at this point. Conventionally, or what we may say traditionally, test charges are positive. So we've got a positive test charge Q0 placed at point P, and then what we do is we figure out, or we measure the net force acting on it due to the surrounding charges. Now let's say the force that it experiences due to the existing electric field is, say, F. Now what we might do is we might define the electric field E at this location as the force acting on the test charge per unit test charge. However, this, even though it's kind of okay, but this is not a very accurate way of describing electric field intensity. Now, why this is not an accurate way of describing electric field intensity is because if this charge Q0 happens to be a fairly large charge, then what it might do is it might displace all the charges around it which are producing the electric field that we are measuring. If it's a large charge, it will exert large forces on surrounding charges, and those surrounding charges might actually move, or it might induce charges in the surrounding objects. If the surrounding charges move or charges are induced on them because of its presence, that alters the electric field which we are measuring. Now it's an established principle that the process of measurement should not alter the measured quantity, and therefore this process is not really very accurate. What we therefore do when we define electric field is, this is kind of approximate. So to get a more accurate definition, what we say is that the electric field intensity is F divided by Q0, while we take a limit of Q0 tends to 0. Now what that means is electric field intensity is a limit of F by Q0 where Q0 tends to infinity. What this means is that we are taking a very, very tiny charge Q0. This test charge is really, really, really tiny, very, very small charge. If it's a very small charge, it will not be able to alter the electric field, because if it's a small charge, it can't exert enough influence on the surrounding objects. It cannot shift their charges, it cannot induce significant charges on them, and therefore the electric field which we are measuring will not be altered by its presence. And therefore this is how we define electric field. So this is a more accurate description of electric field intensity. Now in general, what we tend to do is that if at a given point the electric field intensity is E, if at this point the electric field intensity is E, and at the same point if we place a charge Q, then the force that this charge will experience, the force which this charged particle will experience, it's a point charge, the force which it will experience will be Q times E. That's as per this definition. We've placed a charge Q in place of Q naught and we've shifted it here, so F equals QE. So if at a location there is an electric field E and we place a charged particle carrying a charge Q at that location, then the force acting on it is Q times E. Now this is a classic example of multiplication of a scalar charge with a vector electric field intensity. Now the direction of this force, the product, will be same as that of the electric field intensity if the scalar is positive, and if the scalar is negative, the direction of the product will be opposite to the direction of the electric field intensity. So if Q is positive, then F and E are parallel, and when we say two vectors are parallel, it actually means they're in the same direction. And if Q is negative, it implies that F and E are anti-parallel. And when we say two vectors are anti-parallel, what we're really trying to say is they are in opposite directions. So this then is the concept of electric field, and of course also the electric field intensity E. We will now learn how to calculate the electric field intensity due to charges and distributions of charges. And to start with, we take up the simplest possible case of a point charge. Now for a point charge, we'll be calculating the electric field at a certain distance from the given point charge. Let's say this is your point charge. Let's say it's Q in magnitude, and to start with we are taking up a positive charge. Later we'll talk about negative charge as well. So we are calculating electric field intensity due to a positive point charge. Now electric field intensity, having to repeat this long phrase all the time is tedious. What we generally do is we describe electric field intensity simply as electric field. So electric field from now onwards is a quick method of mentioning electric field intensity. So electric field due to a point positive charge. Now this is your point positive charge. We are looking at a point that's distant r from it. At this point here, we are going to try and find the electric field intensity. Now, to find the electric field intensity here, what we do is we place a positive test charge Q0 and calculate the force on it, this is positive, so there will be a repulsion, and the repulsive force will be 1 by 4 pi epsilon naught q naught by r square. Now when this F is divided by Q naught, we end up with the electric field intensity. And this is 1 by 4 pi epsilon naught Q by R square. Dividing the force by Q naught gives us the electric field intensity. Now, this electric field intensity, mind you, is a vector having this magnitude and it is directed radially away from the charge Q. Now if I take this vector as vector R, then this electric field intensity E is directed along R for a positive point charge. So the direction of E is the same as direction of R, and to indicate that I can multiply this with a unit vector r cap along the direction of vector r. So for a positive test charge, electric field is directed radially outward from the charge. So if we have a positive charge plus Q at any point at all, the electric field would be directed radially outward from it. Of course, at different locations it will have different magnitudes, it will have different directions and so on, but everywhere the direction will be radially outward from it. Now what if the charge was a negative charge? So that's the next discussion. Electric field intensity, or simply electric field, due to a negative point charge. Now this time we have a negative charge, say minus Q, and we are going to calculate the electric field at a distance r from it. So I represent this as a vector r, and we now calculate the electric field intensity at the tip of this vector r. To calculate this electric field, we place a positive test charge Q naught here. The force that it experiences will be directed towards this negative charge. It will be an attractive force, and therefore the electric field is directed towards the charge now. The magnitude of this field can be pretty easily calculated. The force will be 1 by 4 pi epsilon naught Q times Q naught by R square. That's the force, and if you divide the force by Q naught, you get the magnitude of field, and you will notice that the expression for the magnitude of the field is still the same. That hasn't changed. What does change is the direction. This time it is directed radially inward or directed radially inward towards the charge. And to depict this vectorially, what we can do is 1 by 4 pi epsilon naught q by r square, this magnitude can be multiplied by minus r cap, because the direction of the field is opposite to the direction of r. So this direction is opposite to the vector r cap, which is the unit vector in the direction of vector r. So it is directed along minus r cap, and therefore we've multiplied it with minus r cap. That's the electric field intensity due to a point charge. Now a very, very important principle. We revisit the superposition concept, the superposition principle one more time. When we are calculating electric fields due to a number of charges, then the electric field, the net electric field at a given point is simply the vector sum of the individual fields due to the charges present. So there is a revisiting of the superposition principle here. The net electric field at a point is the vector sum of the electric fields due to all the charges in the neighborhood of the point. Now let's say this is the point where we are calculating the net electric field. We have a charged particle Q1 here. Q1 produces an electric field E1 here. Then we have a charged particle Q2 here, and Q2 produces an electric field E2 here. Now E1 is not going to be affected by the presence of Q2 because E1 is produced by Q1, and similarly E2 is not going to be affected by the presence of Q1 because E2 is produced by Q2. So E1 is the electric field of charge Q1 alone, E2 is the electric field due to the charge Q2 alone, and so on and so forth. If we have a number of charges Q3, Q4 and so on, all the way up to Qn, and we have electric fields E1, E2, E3 and so on all the way up to En, then the net electric field at this location will be a vector sum of all these electric fields. Remember, the individual electric fields due to individual charges are independent of the presence or absence of other charges in your given neighborhood, and that's the concept of superposition principle applied to electric fields and electric field intensities. In our next video, we will be applying this concept and calculating electric fields due to various kinds of charge distributions. Thank you very much for watching.